Is this what nuclear war would look like? Many say nuclear war is madness, and the concept known as MAD, mutually assured destruction, has been one of the key reasons that a second nuclear war has not yet eventuated. MAD sums up the ability of nuclear combatants to retain sufficient retaliatory forces to completely destroy the enemy, even after a preemptive strike.
On the European front, General Eisenhower welded his North Atlantic Pact Army together with troops of 11 nations in a force which he hoped to raise to 62 divisions by 1954. European nations are expected to strain their economies to the limit to meet the defense requirements set up in his blueprint. The new laws were the direct outgrowth of a staggering new defense budget of $58 billion. In a world of unrest, Americans shouldered an additional burden in the struggle between East and West, where the race for atomic weapons assumed new proportions and guided missiles took on new importance. The Matador, which someday may carry an atomic charge, was one of America's answers in the armament race, a contest that is the insurance of the free world against slavery.
After the Second World War and the development of the atomic bomb, the United States, Britain, and France, as an independent nuclear power, stood against the Soviet Union. The two sides participated in a Cold War for over 40 years until the collapse of the Soviet Union. Secrets and lies, threats, and dramatic shows of force kept the world on a nuclear knife edge for 4 decades. In that time, both sides built and developed massive arsenals of nuclear weapons and the methodology to deliver them. These superpowers also deployed their nuclear weapons in other countries but retained control. Although attempts were made to restrict nuclear proliferation, other nations slowly developed their own nuclear capability. International agreements restricted the testing of these weapons, first in the atmosphere, then altogether. Nations also fleshed out treaties that restricted nuclear weapons in space, in the Antarctic, and limited the development of strategic anti-ballistic missile programs. Eventually, restrictions on the numbers of weapons in arsenals, then on warhead technology, were also negotiated. Since the fall of the Soviet Union and the end of the Cold War, the great powers' nuclear arsenals have been reduced, old technologies phased out, some stockpiles of warheads even destroyed. But still, there are enough devices to make our entire planet uninhabitable. The world of theoretical physicists, mathematicians, and research scientists has always been a small but close group of brilliant minds. During the 1930s and the rise of fascism, many scientists fled to other countries. Among them was Leo Szilard, a Hungarian physicist and one of the progenitors of the fission process. In France in 1938, a group of scientists studying the fission process believed it was possible to build a fission chain reaction or an atomic bomb. Many began to worry that such weapons were already being developed in Germany. Szilard enlisted the help of Albert Einstein, who signed the now famous letter to the President of the United States, Theodore Roosevelt, warning him about the feasibility of a new type of superweapon and that it might be under development by the Germans. Whoever possessed this nuclear technology would rule the world. Other scientists, including Niels Bohr, also wrote letters to world leaders warning of this nuclear future. Britain had reacted first with tube alloys, the code name for their nuclear program, in conjunction with Canada. When the United States heeded the words of the scientists, they absorbed tube alloys into their own Manhattan Project, which got underway with the atomic bomb now codenamed the Gadget. Simultaneously, a concerted effort was begun to stop the Nazis acquiring or developing this technology through both covert and overt military operations. The principle behind this new weapon was the process of fission. A nucleus, preferably a large unstable isotope like uranium-235, is bombarded with slow neutrons. Only one neutron striking the nucleus will cause it to split into two roughly similar-sized pieces, creating two new, smaller isotopes, plus 2 or 3 neutrons, and a large amount of energy. Based on Einstein's famous formula, E = mc², only a small amount of mass converts into a very large amount of energy. If enough fissile material is packed close enough together, the neutrons released can trigger another two atoms to fission. This then creates more neutrons and energy, which in turn forms a chain reaction and a subsequent detonation. First, the science had to be verified. In 1942, Leo Szilard, Enrico Fermi, and a group of other scientists initiated the first controlled fission reaction of uranium in a cinder block reactor constructed on the squash court of Stagg Field at the University of Chicago. Before 1942, uranium was a rare element found in tiny quantities in laboratories around the world, or a waste product from other mining operations. To manufacture a weapon required large industrial amounts of uranium. The United States had almost none. Some 300 tons. A year's output was available from Canada, but fortuitously, a stockpile of 1,100 tons of uranium oxide was being stored on Staten Island, thanks to mining interests from the Belgian Congo. Once the science of fission was proven, work began on a weapon. Not an easy process. While the design of the weapon was relatively straightforward, the refining of the uranium and plutonium on an industrial scale took time and money. The Manhattan Project first built a massive filtration plant at Oak Ridge, Tennessee, where a filter system to extract the uranium isotope U-235 from the bulk of uranium-238 was devised. A second plant was built at Hanford, Washington. There they manufactured plutonium, another fissile material, theoretically capable of more efficiency than enriched uranium. The Manhattan Project was centered at Los Alamos Laboratory, or Site Y, New Mexico, and at Alamogordo, the assembly and test site, where a massive team of scientists and engineers designed the first nuclear weapons. Led by Dr. Robert Oppenheimer and other brilliant minds, the project settled on two types of fission weapon, the first using highly enriched uranium of the isotope U-235. The process of detonation required a critical mass of fissile material to be rapidly assembled and held together long enough for a neutron source to trigger fission in the material's atoms. A chain reaction would then occur, converting a small percentage of the fissile material into a massive release of energy. Called the gun barrel type, the uranium bomb's design was simple and foolproof. A small subcritical mass of uranium is secured at one end within a strengthened container and surrounded with a neutron reflector. A neutron initiator is placed beneath it, ready to emit a burst of neutrons and initiate the chain reaction. At the other end of the gun barrel, another subcritical mass of uranium in the form of several rings is positioned with conventional high explosives packed behind. Putting it simply, the explosives are detonated, driving the uranium rings down the gun barrel at high speed to the target uranium. Simultaneously, the neutron initiator fires neutrons into the mass to begin the fission process. Scientists were so sure of this device, they did not test it until it fell on the city of Hiroshima, Japan. The second fission design focused on compressing a spherical subcritical mass of plutonium into a small critical mass by way of conventional explosives surrounding the sphere. The core of the bomb is the neutron initiator, a small urchin composed of two materials, beryllium and polonium-210. When crushed, the two metals mix, emitting a burst of neutrons which initiate a fissile chain reaction. Surrounding the initiator is a shell of plutonium weighing about 6.2 kilograms, itself surrounded by a tamper of uranium-238. This tamper reflects neutrons back into the pit to help sustain the chain reaction. Surrounding the pit is a thin shell of boron plastic to protect the core from any straying neutrons. A thick aluminium pusher to compress the pit with the explosive shockwave was the next layer. The explosive composition B surrounded the aluminium shell. Cone-shaped baratol explosive lenses were positioned evenly around the sphere, and a final outer layer of more composition B. A containment vessel or soccer ball of duralumin with brass chimney sleeves retained the numerous explosive detonators. Firing of the explosive detonators milliseconds apart set off the lensing explosives. A spherical shockwave traveled inwards, compressing the aluminium pusher spheres. The pit, the initiator urchin, was crushed, releasing a spray of neutrons into the now critical mass of plutonium. This caused a fission chain reaction, sustained by the still expanding explosive shockwave holding the pit together, until the overwhelming energy released by the fission chain reaction expanded into an atomic fireball. The first device, called Trinity, was detonated at Alamogordo, New Mexico, July 16, 1945. The first nuclear war began on August 6, 1945, and finished 3 days later. As the Second World War approached its critical crescendo, the invasion of mainland Japan, the Allies knew from experience that this was going to be a bloody and costly proposal. Many millions of dollars had been spent on the new super weapon. The US had 2 in their arsenal, and they intended to use them. Serious consideration was given to using one bomb as a demonstration high over Tokyo, and keeping the second in reserve if the first did not scare Japan into surrender. After a long, costly and bloody world war, political and military pressure swung the argument to the alternative, which was to strike a mainland Japanese target and call for surrender. If none was forthcoming, the second weapon would be used. On that fateful date of August 6, 1945, a B-29 Superfortress named Enola Gay, after the pilot's mother, lifted off from the island of Tinian in the Marianas group of islands. Enola Gay carried the first nuclear weapon, codename Little Boy. Its primary target, Hiroshima. The weapon was so successful, it destroyed the entire city of Hiroshima, killing 70,000 people.
Here is the pictorial record of the result. At 0 point, directly beneath the explosion, the soldier in the scene is pointing at the spot from which all damage to the surrounding area was measured in terms of distance from the center of the blast. Within a mile of 0 point, the devastation speaks for itself. But in these very ruins, Army cameramen have found and filmed pictorial evidence that tells in twisted steel and stone the effect of death-dealing atomic power.
The shock and devastation were so great that news of the attack did not reach Japanese authorities quickly. When it did, they could not believe the accounts. US authorities interpreted Japan's delay in responding to their ultimatum as defiance and proceeded with the second attack. 3 days later, on August 9, Boxcar delivered the plutonium bomb codenamed Fat Man to the city of Nagasaki. It killed a further 20,000 people outright. By the end of the year, a further 90,000 succumbed to injury from the 2 attacks. Scientists studied closely the effects of the 2 blasts, in particular the effects of overpressure damage to buildings and structures. The blast also left behind the eerie shadows of humans on sidewalks and fences, burnt in by the intense flash of light at detonation. There was also radiation, both direct lethal doses from the detonation and from the large amount of fissile material and contaminated debris cast into the air and blown about by the winds. This would come to be known as fallout, highly toxic dust and debris that falls downwind from the nuclear detonation, contaminating the ground and water supplies. Of the energy released, 40 to 50% was blast, heat or thermal radiation was 30 to 40%, ionizing radiation accounted for 5%, and the remaining 5% was made up of residue fallout radiation. The US quickly began to research weapon design, but did not build up their arsenal. The following year, Operation Crossroads, 2 detonations with a total yield of 46 kilotons, was conducted in the Pacific at Johnson Atoll. Crossroads was the first underwater nuclear detonation, for which they used war surplus ships and submarines, including captured Japanese battleships, as test subjects.
Temperature at the explosion center is perhaps 100 million degrees Fahrenheit. The terrific pressure caused winds up to approximately 1,000 miles per hour. The radioactive vapor and debris rose to 5 miles.
The first design and efficiency improvement in nuclear weapons was the levitated pit design. When an airspace was put between tamper and pit, the pit was suspended or levitated in the center. A hammer and nail effect was created when the compressing implosion occurred, doubling the yield of the blast. As tests and design improvements continued, the main aim was more efficiency from the fissile material and a reduction in the size of the overall weapon. Here, the United States moved far ahead of the Soviets, reducing the size of their warheads for ballistic missile use. The Soviets with larger warheads had to build larger and more powerful rockets. In a way, this was a negative development for the US, who fell behind in the missile and eventually the space race. In 1951, the US began testing on mainland territory at the Nevada test site in New Mexico. 5 tests of the Ranger series were conducted with a yield total of 40 kilotons. The next advancement was the 2-point linear explosive design. Although very inefficient in respect of fissile material, it did reduce the overall size of the warhead. Again, putting it simply, a solid subcritical mass of plutonium in an elongated football shape is embedded in high explosives. 2 simultaneous detonations occur, one at either end of the cylinder of explosives. With the aid of shock wave shaping baffles, the imploding waves force the plutonium into a spherical critical mass. This design made possible artillery shells and man-portable demolition charges. A further development of this design was the hollow pit and 2 explosive lenses. A hollow sphere of subcritical plutonium is surrounded with a thick tamper of U-235, which is itself surrounded with high explosives. This, in turn, is surrounded by a lens-shaped initiating explosive with a detonator at each end. A much simpler, smaller design, but one with a highly efficient pit and much better yield. The next development was the use of another nuclear reaction, fusion. 2 light nuclei are compressed together under great heat and energy, fusing to form a new, larger element. In so doing, they release more energy and neutron radiation. Isotopes of hydrogen, the lightest of all elements, are used. As in the fusion process of the Sun, the hydrogen is fused into helium. A 50-50 mix of the hydrogen isotope gases tritium and deuterium gas was introduced into the hollow pit of the plutonium. On detonation, the gas would fuse into helium under the heat and pressure of the fission process, thus releasing many more neutrons to boost the plutonium fission chain reaction. This allowed for a quicker chain reaction, needing less high explosive to hold the critical mass together and allowing the removal of the thick uranium tamper. Lightweight beryllium was used as the neutron reflector instead. This design was tested in 1951's Operation Greenhouse and gave yields of up to 45.5 kilotons with a much smaller warhead. The United States thought they had a few years' grace as the world's only nuclear power. But the Americans were shocked when the Soviet Union detonated a nuclear bomb known as Joe-1 on August 29, 1949. Thanks in part to spy Klaus Fuchs, who had been passing on secrets to the Soviets since 1945, their first device was identical to the US bomb dropped on Nagasaki. It would be a further 3 years before the Soviets could detonate a homegrown weapon. The Buster Jangle series in Nevada in 1951, 7 blasts in all, many with troops on the ground, looked at the capability of soldiers to deal with a tactical nuclear strike.
The tremendous detonation, felt 260 miles away, shakes the earth under the soldiers, and the blast fills the air with flying dust. The test is a terrifying experience, but it shows that the atom bomb can be used in support of troops.
Now that the US had to contend with a nuclear-armed foe at the other end of the socio-economic spectrum, Civil defense became a major concern among the population. The government tried to ease fears of red aggressors by releasing several handy films on self-protection from the nuclear threat, all highlighting sensible action to be taken during a nuclear attack.
Every one of us must remember to do the same thing. That's what this film is all about. Duck and cover. We all know the atomic bomb is very dangerous. Since it may be used against us, we must get ready for it, just as we are ready for many other dangers that are around us all the time. You know the places marked with the S sign? They're safe places to go when you hear the alarm. If there is a warning, you will hear it before the bomb explodes. But sometimes, and this is very, very important, sometimes the bomb might explode without any warning. Then the first thing we would know about it would be the flash. And that means duck and cover fast, wherever you are. There's no time to look around or wait. Be like Bert. When there is a flash, duck and cover, and do it fast.
1952 saw the United Kingdom test its first atomic weapon in Operation Hurricane. Britain tested a total of 45 weapons in Australia and some in the US.
Photographed from 13 miles away, the familiar atomic mushroom pours its deadly cloud of radioactive vapor toward the sky.
The Tumbler Snapper series of tests, a total of 7 above-ground detonations, introduced new designs including boosted warheads. In 1952, on the Pacific Proving Ground, Mike, the first so-called hydrogen bomb, is test-fired.
And the United States set off the most awesome weapon of all, the hydrogen bomb. The searing atomic blasts punctuated an event-packed year, a year of which historians of the future may well say, it was a year of destiny.
The fission bomb can give a yield of up to hundreds of kilotons, but increasing the yield even further into the megaton range required a secondary or add-on fusion component. The famous Edward Teller and Stanislav Ulam, two key nuclear scientists, solved the design problem in 1951, as demonstrated by the Mike shot during Operation Ivy at Enwitok in the Pacific a year later with a 10.4 megaton detonation. The radiation implosion harnesses the X-ray energy of an exploding fission bomb to compress and superheat a hydrogen isotope source bonded within the metal lithium deuteride. In a very short time, the hydrogen isotope is released from the metal and fused into helium nuclei, which release vast amounts of energy. The first design consisted of a hollow cylinder of low-cost U-238 surrounding a hollow cylinder of lithium deuteride. In the center of the flute, as it was known, was the fissile trigger of either plutonium or U-235. The flute was 59 centimeters long with a diameter of 38 centimeters, all encased in polystyrene foam. The primary fission weapon is detonated. The massive X-ray energy turns the polystyrene into high temperature and pressure plasma. The plasma compresses the flute and superheats it. This forms the hydrogen element, which begins to fuse into hydrogen, releasing still more neutrons that cause the spark plug in the center to fission almost completely. This releases yet more neutrons and X-ray energy sufficient to cause the relatively inert tamper of U-235 to fission, releasing most of the destructive force of the entire device. Although the fusion process of hydrogen is part of the overall device, it is in fact the fission process that generates most of the destructive force.
The gun crew moves back to take positions in slip trenches during firing. The time is 08:30.
With the reduction in size of the basic weapon, artillery piece-sized bombs are tested at the Nevada test site. 11 detonations with atomic Annie.
Accuracy 4 times greater than any gun developed before World War II. The 280-millimeter gun has proven...
In August of the same year, the Soviets tested their 4th nuclear device.
Some 13 miles under any weather conditions.
In 1954, 6 detonations codenamed Castle were made in the Pacific using deployable warheads. One test of a thermonuclear device yielded twice the expected power, contaminating a large area of the Pacific Ocean with fallout.
100-inch camera is...
Teapot was the code name for 14 more 1955 detonations, this time of devices designed at the Lawrence Livermore National Laboratory.
The familiar mushroom cloud snakes skyward, hurling the atom's deadly radiation high into the heavens.
Also in that year, the Soviets detonated their first so-called hydrogen bomb. In 1956, the US ran Operation Red Wing, in which they used all 3 bomb design developments: 2-point linear detonation, gas fusion boosted pit, and the latest development, the air lens. Incorporating the nail and hammer effect again, a hollow ovoid high explosive is detonated from either end. The imploding shockwave moves through the air, forming a spherical wave. The wave hits and detonates a spherical charge that then crushes the plutonium pit. The initial fission process is boosted with the fusing hydrogen gas, and the weapon detonates. This so-called Swan device was small, only 30 centimeters in diameter. Efficient in both effect and materials, it evolved into the W-54 warhead and became the basis of most other weapons designs. It would become the primary trigger for the secondary fusion-fission device or thermonuclear bomb, known incorrectly as the hydrogen bomb. 1957 brought Operation Plum Bob at the Nevada test site, 29 tests, including use of troops on the ground, where many were exposed to hazardous levels of radiation. This same year, Britain tested its first hydrogen bomb.
Britain fires its first H-bomb to join the United States and Russia as ranking atomic powers. The thermonuclear device was fired high over its target in the Christmas Islands, keeping fallout at a minimum. But the test added heat to the mounting debate over the safety of atomic tests.
The following year, a planned series of thermonuclear detonations to dig a new harbor at Cape Thompson in Alaska was cancelled due to public pressure. Operation Heart Attack 1 and 2 saw the US detonate a total of 72 nuclear weapons, each a minimum of 1 megaton in range, in Nevada and the Pacific. Argus was the launching of 3 Redstone missiles armed with nuclear warheads over the southern Atlantic Ocean. They detonated in near space.
The 3 rockets fired by the vessel about that time to explode nuclear bombs 300 miles high as part of Project Argus, the greatest scientific experiment ever conducted. The nuclear bursts in the vacuum of space threw a shell of radiation around the Earth within an hour. A globe-girdling network of thousands of scientists made observations. To monitor the radiation shell in outer space, the satellite Explorer 4th was launched.
France began testing its nuclear device in 1960 in Algeria. 4 weapons were tested. One story suggests that the last detonation was not so much a weapons test as an emergency procedure to stop the bomb falling into the hands of guerrilla forces rebelling against the French. 1960 saw the world's stockpile of nuclear weapons climb. The US had 20,434 strategic and tactical warheads. The Soviets were far behind with 1,605, mainly large thermonuclear devices, and Britain had developed its own designs with an arsenal of 30 weapons. To maintain a viable deterrent from a first strike by the Soviets and vice versa, the US had submarines patrolling the depths of the oceans, missiles in their silos poised and ready, and bomber aircraft in the air patrolling their fail-safe points 24 hours of the day. But of course, accidents are going to happen. The most likely to occur involved aircraft, and there were several.
An atomic bomb breaks loose from a mounting shackle in a B-47 jet over Florence, South Carolina, plummets to Earth, causing a sensational freak accident. There was near disaster for those within range of the TNT, that is the bomb's trigger. 6 were injured. The home of Walter Gregg was turned into a shambles.
In October 1961, the Soviets detonated a gravity bomb called the Tsar Bomba at 50 megatons, the largest weapons test ever.
Polaris missiles arrive at Cape Canaveral for their first test firings from the nuclear submarine expressly designed for the job, USS George Washington. The tests are a stirring climax to a 4-year program to mate the nuclear submarine and the intermediate range ballistic missile. Now the sub's missile hatches are cleared and ready. They'll house the 28-foot 2-stage rockets until the moment when mighty gusts of compressed air will shoot the Polaris from under the sea to the surface and ignition. Every stage of the loading and the cruise to the firing area about 30 miles off Cape Canaveral is under detailed scrutiny of a battery of test instruments. The George Washington goes down some 50 to 60 feet below the surface, and the time for launching is at hand. Missile, after a startling off-angle emergence, corrects itself and soars downrange 1,100 miles to its target with remarkable accuracy. A few hours later, the second Polaris is fired. Another successful shot, an achievement of major strategic importance for America's defense.
At the same time, Dominic tests were performed at Christmas Island, Johnson Atoll, and the Central Pacific. A total of 36 shots, including Frigate Bird, the live fire of a Poseidon missile with a live warhead, plus Fishbowl, 3 high-altitude detonations. During this series of Thor missile tests that several accidents and mishaps occurred, the most serious the Bluegill prime shot. The Thor missile's main engine failed on the launch pad and caused a fire. Range safety officers destroyed the missile and warhead on the pad, seriously contaminating the entire site, requiring 3 months of decontamination and repairs. Detonated a further 12 weapons underground in Algeria. The partial test ban treaty signed between the United States and the Soviet Union in 1963 called for the cessation of atmospheric tests and a limit to the maximum yield of warhead tests. It allowed for underground testing. January 1966, and a fully armed B-52 bomber carrying 4 B-28 megaton range gravity bombs collided with an air tanker whilst refueling over Palomares, Spain, killing the crews of both aircraft and destroying 2 of the bombs, which contaminated a large area with plutonium. 2 other bombs went missing, and sparked a massive bomb hunt.
We've just seen the H-bomb. It was
each with multiple warheads aboard ballistic missile submarines in their strategic arsenal, plus thousands more tactical warheads for short-range missiles, torpedoes, depth charges, anti-ship missiles, artillery pieces, and even man-carried Davy Crockett recoilless rifle and demolition charges. The modern design layout for these weapons to gain the most efficiency for their size comes from a spherical secondary physics package. It is far more efficient than a cylindrical design for the modern warhead like the US W-88 type model represented. The primary is as earlier described, a two-point hollow-pit fusion-boosted fission warhead. The secondary is a hollow spherical design layered from outside to inside with a U-235 tamper, pusher, lithium-6 deuteride fusion material, a U-235 spark plug fission device that triggers the fusion of the core of lithium-6 deuteride. The entire assembly is encased in polystyrene foam and an outer casing of U-235 for added punch. The primary booster gas reservoir has to be replaced from time to time as the gas deteriorates over time. The W-88 was the last weapon designed by the US and is fitted to the US and British Trident D5 missile. As ballistic missiles developed with improvements in throw weight and the reduction in size of warheads, the multiple re-entry vehicle missile warhead was developed. Simply described, several small nuclear warheads could be housed in the nose cone of a missile. Arranged in a bus, they could be dispersed separately from the final stage of the missile's flight. They could also be accompanied with decoys and other target penetration aids. These MIRVed warheads ranged from 3 by 350 kilotons, as for the Minuteman III missile, up to 10 warheads aboard the new MX missile system. Sea-launched missiles were also equipped with multiples of up to 6 warheads. The next stage was MIRVed warheads, or multiple independently targetable re-entry vehicles. Whereas a MIRVed payload functioned more like a shotgun effect dispersing warheads, the MIRVed warhead could maneuver in space and deploy its warheads to individual targets within a wide range of the missile's flight path. The next development was MARVed warheads, which, once deployed to their designated target, could maneuver to avoid any countermeasures deployed to defend a target site. These re-entry vehicles, combined with radar decoys and other penetration aids, including dummy warheads, made any missile defense system useless. Treaty negotiations quickly included these new developments to help maintain the mutual balance of power. Air-launched cruise missiles were another development for nuclear delivery. Bombers no longer needed to penetrate deep inside enemy territory. They could fly to the enemy border, then launch a salvo of long-range, terrain-following cruise missiles. These too were limited in future treaties. From 1970 to 1992, test shots at Nevada totaled 399, plus one detonation in Amchitka, Alaska, and Rio Blanco. Series names like Tinderbox, Guardian, and Grenadier tested and refined these weapons. These shots included the 1965 Charioteer test of a Mark 21 RV that breached containment and released radiation, 2,000 times more than 3 Mile Island. India joined the growing fraternity of nuclear powers May 1974, detonating a plutonium implosion device with a yield of 6 to 20 kilotons underground at Pokhran. They tested a total of 5 or 6 devices. Further US tests included Musketeer, Touchstone, and Sculpin until the Julian tests of 1992. The last was Divider on September 23rd. The Soviets ceased weapons testing October 24, 1990, and the British tested their last device in 1991 down a mine shaft in Bristol. The French tested a further 146 devices in the Pacific until their final one in January 1996. In reaction to India, Pakistan also began developing nuclear weapons in 1972. They have carried out 6 weapons tests, the first in May 1998, believed to be the fusion-boosted uranium designs with a low kiloton yield. Although Israel declines to comment, it is believed she possesses a stockpile of 200 tactical nuclear weapons, and both intermediate-range ballistic missiles and fighter aircraft to deliver the warheads. South Africa is also believed to have constructed up to 6 uranium gun-type weapons, but has since dismantled them. On September 22, 1979, the US and Soviet Union surveillance satellites detected a nuclear detonation in the atmosphere off the southern coast of South Africa. It is suspected it was a joint Israeli-South African effort, but both deny any involvement. The latest nuclear club member is believed to be North Korea. Secrecy surrounds their program, but it is believed they detonated an underground explosion with a yielder from 0.19 to 1 kilotons at their Pongji test site on October 9, 2006. Currently, the Russian Federation holds the largest strategic nuclear stockpile. Their strategic rocket forces currently comprise 75 SS-18 or R-20 Satan missiles. Introduced in 1975, they are silo-based with up to 10 MIRVed warheads. 126 SS-19 missiles, either silo or mobile-based with 6 MIRVed warheads. 306 SS-25 mobile-launched missiles, each with a single warhead. And 65 SS-27 or Topol-M missiles with either single or multiple 550 kiloton warheads. This missile will eventually replace the earlier model, SS-25. In ballistic missile submarines, they boast a total of 26 boats, 13 Delta armed with SSN-18 missiles for a total of 208, each MIRVed with 3 warheads of 200 kilotons. 6 Typhoon-class boats with 20 SSN-20 missiles, each with up to 10 MIRVed 100 kiloton warheads for a total of 120 missiles. Another 112 SSN-23 missiles, 4 MIRV 100 kiloton on 7 Delta submarines. The weakest link of their nuclear forces has always been their bomber fleet. They retain 63 Tu-95 Bear bombers, each capable of carrying between 6 and 16 air-launched cruise missiles or short-range attack missiles. They also operate a fleet of 6 Tu-160 bombers, armed with between 6 and 16 weapons in the 250 kiloton range. The current arsenal of the US is officially 9,960 warheads, but only 5,735 are operational, with 5,021 of these strategic. Under the Moscow Treaty, this number will be reduced to a maximum of 2,200 strategic warheads by 2012. Currently, silo-based missile forces consist of the Minuteman III missile with 500 in operation, soon to be reduced to 450, 400 with a single warhead, and 50 with 2 MIRVed warheads. The MX missile, which had up to 10 warheads per missile introduced in 1986, have all been removed from service. Their W-87 warheads to be fitted to the remaining Minuteman III force. Ohio-class submarines have been reduced by 4 to a total of 14 boats. Each can carry up to 24 Trident D2 missiles, each capable of 6 MIRVed warheads. The strategic bomber remains a major force for the US, still fielding the aging B-52 bomber and the newer B-2. Each can carry gravity bombs or cruise missiles. 76 B-52s are considered on active duty, the majority, if not all, nuclear capable. The B-1 bomber has been withdrawn from strategic nuclear service and will only be armed with conventional weapons. The other 20 B-2 stealth bombers remain in operation, able to carry 16 B-83 nuclear weapons capable of up to 1.2 megaton yield. 14 Ohio-class boats, each armed with 24 Trident missiles capable of up to 6 warheads per missile, is the single largest component of the US's strategic weapons platforms. The 3 stages with solid fuel rocket motor can deliver its payload up to 11,300 kilometers, a total of 12 MIRVed warheads of the W-88 type. But this has been reduced under the START 1 agreement to a limit of 8 warheads, and SORT will reduce them further to 4 or 5. The US will also reduce its tactical stockpile to 500 warheads, a mixture of 100 Tomahawk cruise missiles and 400 B-61 gravity bombs. French nuclear forces did include silo-based intermediate-range missiles and short-range mobile theater missiles, all of which have been retired since the fall of the Soviet Union. But France maintains a retaliatory force in its submarine fleet of ballistic missile boats. They have 4 L'Inflexible class boats, each carrying 16 missiles MIRVed with 6 warheads in the 150 kiloton range. A new class of boat, Le Triomphant, was launched in 1996. Currently 1 boat with 16 missiles, each MIRVed with 6 100 kiloton warheads. The French Navy retains carrier-based aircraft capable of nuclear weapons delivery and is believed to retain 45 SRAMs, each with a yield of 300 kilotons for its Mirage 2000 and another 24 SRAMs for its fleet of Super Étendard aircraft. British nuclear forces have been reducing their stockpile and type of weapons for many years, in particular since the demise of the Soviet Empire. They retain a deterrent fleet of just 4 Vanguard-class submarines, each armed with 16 Trident II D5 missiles, each MIRVed with 3 warheads supplied by the United States, for a total of 48 warheads per boat. The British government retains just 200 or fewer strategic and tactical nuclear warheads. India has 30 to 35 warheads, deliverable by medium-range missile or bomber aircraft. Pakistan retains 24 to 48 warheads dispersed throughout the country. Although the threat of all-out nuclear war has receded greatly over the last few years, stockpiles are being effectively reduced, and the proliferation of nation-states with nuclear weapons closely watched, there appears a new danger in the nuclear world. Non-state organizations, terrorist groups, are attempting to acquire this technology or one of the other so-called weapons of mass destruction. Today, more than ever, the threat of a limited nuclear war is far less likely than a single terrorist act in a major Western city with a purchased or stolen nuclear weapon. The world must remain vigilant and not allow this to happen.
Race, a contest that is the insurance of the free world against slavery.
After the Second World War and the development of the atomic bomb, the United States, Britain and France, as an independent nuclear power, stood against the Soviet Union. The two sides participated in a Cold War for over 40 years until the collapse of the Soviet Union. Secrets and lies, threats and dramatic shows of force kept the world on a nuclear knife edge for 4 decades. In that time, both sides built and developed massive arsenals of nuclear weapons and the methodology to deliver them. These superpowers also deployed their nuclear weapons in other countries but retained control. Although attempts were made to restrict nuclear proliferation, other nations slowly developed their own nuclear capability. International agreements restricted the testing of these weapons, first in the atmosphere, then altogether. Nations also fleshed out treaties that restricted nuclear weapons in space, in the Antarctic, and limited the development of strategic anti-ballistic missile programs. Eventually, restrictions on the numbers of weapons in arsenals, then on warheads. This then creates more neutrons and energy, which in turn forms a chain reaction and a subsequent detonation. First, the science had to be verified. In 1942, Leo Szilard, Enrico Fermi, and a group of other scientists initiated the first controlled fission reaction of uranium in a cinder block reactor constructed on the squash court of Stagg Field at the University of Chicago. Before 1942, uranium was a rare element found in tiny quantities in laboratories around the world, or a waste product from other mining operations. To manufacture a weapon required large industrial amounts of uranium. The United States had almost none. Some 300 tons. A year's output was available from Canada, but fortuitously, a stockpile of 1,100 tons of uranium oxide was being stored on Staten Island, thanks to mining interests from the Belgian Congo. Once the science of fission was proven, work began on a weapon, not an easy process. While the design of the weapon was relatively straightforward, the refining of the uranium and plutonium on an industrial scale took time and money. The Manhattan Project first developed. Other scientists, including Niels Bohr, also wrote letters to world leaders warning of this nuclear future. Britain had reacted first with tube alloys, the code name for their nuclear program, in conjunction with Canada. When the United States heeded the words of the scientists, they absorbed tube alloys into their own Manhattan Project, which got underway with the atomic bomb now codenamed the Gadget. Simultaneously, a concerted effort was begun to stop the Nazis acquiring or developing this technology through both covert and overt military operation. The principle behind this new weapon was the process of fission. A nucleus, preferably a large unstable isotope like uranium-235, is bombarded with slow neutrons. Only one neutron striking the nucleus will cause it to split into two roughly similar-sized pieces, creating two new, smaller isotopes, plus 2 or 3 neutrons, and a large amount of energy. Based on Einstein's famous formula, E = mc squared, only a small amount of mass converts into a very large amount of energy. If enough fissile material is packed close enough together, the neutrons released can trigger another 2 atoms to fission. Is this what nuclear war would look like? Many say nuclear war is madness, and the concept known as MAD, mutually assured destruction, has been one of the key reasons that a second nuclear war has not yet eventuated. MAD sums up the ability of nuclear combatants to retain sufficient retaliatory forces to completely destroy the enemy, even after a preemptive strike.
On the European front, General Eisenhower welded his North Atlantic Pact Army together with troops of 11 nations in a force which he hoped to raise to 62 divisions by 1954. European nations are expected to strain their economies to the limit to meet the defense requirements set up in his blueprint. The new laws were the direct outgrowth of a staggering new defense budget of $58 billion. In a world of unrest, Americans shouldered an additional burden in the struggle between East and West, where the race for atomic weapons assumed new proportions and guided missiles took on new importance. The Matador, which someday may carry an atomic charge, was one of America's answers in the armament.
Warhead technology were also negotiated. Since the fall of the Soviet Union and the end of the Cold War, the great powers' nuclear arsenals have been reduced, old technologies phased out, some stockpiles of warheads even destroyed. But still, there are enough devices to make our entire planet uninhabitable. The world of theoretical physicists, mathematicians, and research scientists has always been a small but close group of brilliant minds. During the 1930s and the rise of fascism, many scientists fled to other countries. Among them was Leo Szilard, a Hungarian physicist and one of the progenitors of the fission process. In France in 1938, a group of scientists studying the fission process believed it was possible to build a fission chain reaction or an atomic bomb. Many began to worry that such weapons were already being developed in Germany. Szilard enlisted the help of Albert Einstein, who signed the now famous letter to the President of the United States, Theodore Roosevelt, warning him about the feasibility of a new type of superweapon and that it might be under development by the Germans. Whoever possessed this nuclear technology would rule the world.